Hi everyone, in this video we're going to be going through a couple examples on the lecture guide for Module 6. We're going to start with example 1 and do a few of these. So this is a review trying to make sure we're okay with picking out variables, populations, making sure we're okay categorical quantitative, because remember that's going to tell us if we use pi or mu, p hat x bar, and that's really important going forward. So the first one says, I want to know the average GPA of all students at DCC. So I randomly ask 150 students to report their GPA. What's the variable? Well, what am I asking of each student? I'm asking for their GPA. What's the population? Well, what's the big group that I want to learn about? I want to learn about all students at DCC. My sample? Well, remember the sample is just the smaller group, the smaller subset of the population you want to learn about. Well, I ask 150 students, so that's my sample. The parameter of interest is the average GPA, and that's mu because it's an average. This is quantitative. It's again because it's an average. The data I'm getting back, they're all numbers. You have a GPA of 2.5, of 3, of whatever it is. And on top of that, you can average those numbers and it still makes sense to say the average GPA. So that's all pointers to quantitative. And then finally, the symbol for the statistic is x bar. So over here, we've got x bar. Remember, parameter, we have a Greek letter. Statistic, we have our alphabet's letter with a little hat on it. So x with a little hat on it. Okay, let's try the next one. I want to know the percent of all college students who prefer Iron Man over Batman, so I talked to 75 students from several colleges and asked them variable. So the variable is, do you prefer Iron Man or Batman? From each student, that's the information I'm getting. They're going to tell me either Iron Man or Batman. What's the population? Well, the population's all college students. That's what I'm interested, that's the who I'm interested in learning about. The sample. Okay, so out of that big group of all college students, who did I actually talk to? I talked to 75 students. What's the parameter of interest? Well, I'm interested in knowing the percentage of all students who prefer Iron Man over Batman. And that's pi because it's a percent proportion. Okay, this is categorical, again, because we're using proportion. What does our data look like? It's either going to look like Iron Man, Batman. These are categories, so it's categorical. And remember, for categorical variables, we're going to use p hat as our statistic. So p for proportion, hat because it's a statistic. Okay, so for example 2, we are diving back into section P.2 to talk a little bit more about means, medians, standard deviations. So this problem is all about the standard deviation. And so it says consider 3 students with the following distribution of 24 scores each. So each of them are in a class where there were 24 quiz or homework scores, whatever you want to think of these as. And we are going to try to understand their scores, their distribution of scores, by looking at some of these terms, these numbers. Okay, so it says put the students in order from smallest standard deviation to largest standard deviation. And then it adds to that, can you calculate the standard deviation exactly for any of these students without a calculator? So I've said in the past, we're not really going to look at the formula for standard deviation. It's just too much for us to worry about right now. You can look it up if you want to. It's not too bad, but it's just not necessary when we have calculators. But there is one student here where we can actually just tell you what the standard deviation is with no real work. So let's go through and see if we can find it. So let's start with Amanda. So Amanda's scores were 8 across the board. So 8, 8, 8, 8, 8 all the way through. Okay, so let's think about Amanda and her standard deviation. So standard deviation was our way of measuring spread of the data. So the more spread out your data is, the bigger your standard deviation will be. Well, let's look at Amanda. Okay, so is there any spread in Amanda's scores at all? No, there's not any spread. They're all the same exact value. So if the standard deviation is supposed to measure spread, and there is no spread, then that means there is no standard deviation. To be more specific, it's 0. So if the standard deviation is 0, it means there's no spread at all in your scores. And that's what's happening for Amanda. She is completely consistent 8 every time. So that's what it says here. The average for Amanda's scores is 8, so there is no spread, so her standard deviation is 0. That is the smallest you can get. The absolute minimum standard deviation is 0, which means no spread. So we are immediately going to put Amanda in here first because we want to do smallest to largest. So right here, smallest to largest. Okay, so let's think about Barney now. There's clearly some spread in Barney's scores. On the low end, he had a 5, and on the top end, a 10. Okay, so there's definitely difference there, so we're going to have some standard deviation. So in order to actually figure this out, like really get the idea, or if we wanted to actually do the calculation, we don't just look at the spread. The standard deviation is built so that you first look at the mean of your data, then you measure how far each data point is from the mean, and you collect those distances. So it's not just that I care about the difference between 6 and 9 or 6 and 10. I don't care about that specifically. I care about, okay, find the middle, the mean here. Then I want you to look at how far away I am from that middle. So for Barney, you could do the calculation if you want, but we should get a mean of about 7.5. All right, we've got about half of the values lower than 7.5, half of them higher. So we're going to guess that 7.5 is the mean. So then we want to look at, okay, what's the spread like? Well, 8 is pretty close to 7.5, so not much spread there. So all these values really aren't giving you too much spread, so that's not going to make the standard deviation get too big. 9 is really not that far from 7.5 either. The furthest we get is 10, and that's really not too far either. Same with the other way. 7's really close. 6 isn't too far, and 5 is about as far as we get as well. So that's 2.5 off. So overall, Barney has some standard deviation here. It's bigger than 0. There is some spread, but he's not too far away from the middle, if the middle is 7.5. So, okay, that's what we said here. The average is 7.5. There is some spread, but it's not going to be too bad. So we're not sure where to put Barney. Definitely bigger than Amanda, but what about Charlene? So we'll look at Charlene. Charlene has a ton of spread in her scores. She's got a bunch of scores that are 0 and a bunch that are 10s. So how do we figure out the actual standard deviation here? We find the middle value. If we average these numbers together, all these numbers up together, we're going to get about 5. Okay? So if you add all these up and divide by 24, you're going to end up getting 5. So then here's the idea. The standard deviation is you're, in some sense, taking every data point and saying how far are you from the average, and then you're adding those up. It's not perfectly that, but it's about that. So look what happens. If my average is 5 right here, then 0 to 5, that's a big jump. The distance between 0 and 5 is 5. Look at for Barney. We never even got close to that. The furthest we had to go was from 7.5 to 5. That's only a jump of 2.5. For Charlene, every single data point is a whole jump of 5. 0 to 5, 0 to 5, 0 to 5. What about over here? 10 to 5, 10 to 5. That's also a jump of 5. So Charlene has a much bigger standard deviation because every one of her data points is pretty far from the mean. Barney has got a lot of data points that are pretty close to the mean. Amanda has every data point right on top of the mean. So that puts Charlene at the largest standard deviation. So for example 4, we are looking at the scenario where we've created a 5-question quiz on solving algebra equations. We gather 100 random students from the cafeteria and have them take the quiz. Then we gather 100 random students from the afternoon sections of calculus and have them take the quiz. So part A says, which group do you expect to have the highest mean score? So what's the highest average? So our answer to this is the calculus students. Well, why? Well, what's going to make a set of scores have a high average? If a lot of the scores are high. So we need a lot of really good scores to have a high average. Okay, well, algebra is something that you've definitely taken if you do calculus and you use it in calculus. So these calculus students have successfully taken algebra and are consistently using that as well. So then if that's true, they should be able to do well on the quiz. So there you go. They're going to do well. They should have high scores. Their mean should be high. So on the other hand, the DCC cafeteria students, here's the thing. There could be calculus students or students who have taken algebra and been successful in the cafeteria, and they're probably going to do well, okay? But you're also going to have students in the cafeteria who haven't taken a math class in a long time, or who haven't ever even taken algebra possibly. So those students will not do as well, and so you will have some of those 100 scores be low. But in the calculus, you're going to have almost all of them be really high. And so when you're just talking about the average, the calculus student's average will be higher. Okay. What about B? B says, which group do you expect to have the highest standard deviation, the most spread? So we actually already answered that in the discussion we just had in A. The DCC cafeteria students will have some calculus students, some algebra students, and some students who haven't done math in a long time. That is going to mean that they have a larger spread of scores, some high, some low, some in the middle. The calculus students are mostly going to have high scores, so they're all packed together on the higher range, which means they'll have less spread because they're more packed together. In example 5, we're looking at the question, do children prefer candy more or toys more for a Halloween treat? We looked at 5 households in Connecticut, 5 neighborhoods in Connecticut, offering children 2 plates, one with candy, one with toys. We sampled 283 children, 148 took candy, 135 took a toy. So A asks us to identify the null and alternative hypotheses as well as the statistic. So the first thing we have to do is identify our parameter. We are interested in the proportion of children who prefer candy over toys. We're going to call that pi. Now, could you have said, let's let pi be the proportion of children who prefer toys over candy? Sure, it's up to you. There's 2 options. You can pick whichever one you want to think of as the success. I'm going to say choosing candy as our success in this case. So what's the null? The null is there's no preference. Children like toys and candies equally. So that would be that the proportion of children who prefer candy over toys would be 0.5 or 50%. Right? They're just randomly picking. Doesn't matter. What's the alternative? Well, the alternative is there is a preference. They do not have an equal preference for this, right? They either like candy more or toys more, but we don't know which one, so that's why we use not equal to. Okay, not equal to, because we don't know if it's candy more or toys more. And our statistic is, because we're focusing on candy, 148 out of 283, or about 52.3% of the children we looked at wanted candy over a toy. Okay, so it says, use the applet to conduct a simulation, identify the standard deviation of the null distribution. So this is our original applet. We know how to do this. You put in 0.5, you put in 283 for your sample size, you'd say 1,000 dots, 100 dots, whatever. This is the picture that I produced, so make sure you practice this and you get a picture that's similar looking. Your mean and standard deviation may be a little bit off from me, but it should be very close to this, and the picture should look similar. The standard deviation we got was 0.029. Okay, we're going to come back to this. C says, explain why we can use a theory-based approach for this example. So since this is categorical, right, we're using pi and p hat, we need to make sure that we have at least 10 successes and 10 failures in our sample. Okay, so 10 successes, 10 failures. That means, in our case, we needed at least 10 kids to choose candy and 10 to choose toys in our entire sample. And we got that pretty quick because we asked so many kids. We had 148 candies and 135 toys. So we definitely have both bigger than 10. We can use the theory approach. So let's do it. Okay, So the first thing that we need to do here to use the theory-based approach is to find our standard error. Let's remind ourselves, what's the standard error? Let's go back up to this picture. The standard error is the spread of this distribution, the sample distribution. So when we simulated, we got this number, but we're going to use the theory-based approach so we don't even have to simulate, and we can predict this number. So what I'm saying in this piece and in just the entire module is that we can predict what this number will be and what this number will be without even doing the simulation. So the part we're on, we're going to predict this number here. So let's do it. The formula is the square root of pi times 1 minus pi over n. Pi comes from the null hypothesis. What did you say for the null? N is our sample size. So we said 0.5 was our null hypothesis value. So I plugged that in here. And then we asked 283 kids to pick between candy and toys. That gives me 0.0297. Let's go back up. 0.029, and then they rounded or were very close, and maybe it was 0.0294, so they rounded to 29. So very, very close. All we did was one simple calculation. The computer had to simulate the sample of 283 kids 1,000 times to get this number. We plugged it into one quick formula and were able to get something very close. So pretty crazy. So let's use that. We then want to find the standardized statistic. Well, what's the formula? It's the same formula as from before, right? Statistic minus the mean of the null over the standard error. My statistic was 148 out of 283. That's the candy. Minus the mean of the null from the null hypothesis, which was 0.5, divided by the standard error that I just calculated right here. And here's my z-score, 0.773. So that's pretty small, right? Okay, so that's a pretty small z-score, which means small z-score, null is plausible. So it's plausible that the kids care about 50-50. Doesn't matter to them. They're just randomly choosing. Right? There's no real preference between candy and toys for these kids. Okay, but if we were going to do this using the simulation, like in Unit 1, do we get the same thing? Well, this is the distribution we had. We have the computer take our statistic, and then we do more extreme in both directions, so right and left. We get a p-value of 0.457, which is huge, big p-value, and a big p-value says the null is plausible. It agrees. I also here just did a z-score just so you could kind of see what it looked like to pull the information directly from the simulation, and we got a z-score of 0.86. It's not exactly what we got here, but they're pretty close, and they give the same idea. The null is plausible. So, we got it. We end up getting the same conclusion from both the simulation and the theory. Woo! Okay, for example 8, we have a website reporting that the average or mean monthly grocery budget for a family of 4 in the U.S. is $695 per month, with a standard deviation of $35. So we are Maria, we are interested in determining if this average is true for her own area. She collects a random sample of 115 families and finds they have an average of $710 for groceries a month, with a standard deviation of $32. So, describe the variable including if it's categorical or quantitative. So for this problem, we are quantitative because the problem said we wanted the average or mean, right? And so another way to think about that, what's the data look like? It's dollars, that's numbers, we can average it. Okay, what's the parameter of interest? So the parameter of interest is the average monthly grocery budget for a family of 4 in the U.S. And because this is quantitative, because it's a mean, we're using mu. This is unknown, but we do have a claimed value we found on the internet that we're going to test. But in general, we don't know if it's true or not. You can't just believe everything you read on the internet. Okay, so I says each of these numbers, find out what symbol goes with it. So 695, let's go back up here. That was our claimed value. So that's going to be mu, but remember, that's only the value for mu in the null hypothesis, which you can see below. We don't actually know if that's the true value of mu, but that's our claimed value. 35 was the standard deviation, the claimed population standard deviation. That's sigma, Greek letter because it's parameter. N is 15. Our sample size is 15, the 115 families. X bar is 710, average of $710. Standard deviation of 32, but that's for our sample, so that's little s. Okay, let's write out the hypotheses. So our null hypothesis is that the online resource is correct and the average monthly grocery budget is $695. So we're saying, okay, we believe you, online source. The alternative is, no, I don't believe you, online source. The average is not $695. And I don't know if it's bigger in my area or smaller, so I'm just looking for evidence that it's not $695. Okay, so then what we could do, what we've done in the past, is we could run a simulation assuming the null hypothesis, and then we could compare our statistic to that, find the p-value, the standardized statistic, all unit 1. What we're doing here, though, is instead of that, we are going to use the theory to produce the same picture we would have gotten in the simulation, but we're going to do it all by hand using the theory. So you'll see the picture in just a sec. We'll fill it out. The first thing we have to do, though, is figure out, okay, well, how spread out is this picture going to be? And the way we do that is by finding the standard deviation of the sampling distribution. Remember, we called that the standard error. So all we're doing in part K is finding the standard error. The formula for quantitative is given here, right? So let me zoom in a little bit more. It's sigma divided by the square root of n. We already labeled these. 35 was our claimed population parameter for the standard deviation. 115 was our sample size. I plug that in, I get 3.26. So, how do I use this? So I claimed that it was how spread out my sampling distribution should be. Okay, great, but how do I use that to make a picture, right? Well, what do we know about the picture? It's supposed to have in the middle our claimed null hypothesis value, which was 695. So that's supposed to be the middle of our picture. Every simulation we've ever done, right? The middle of the picture is almost perfectly, not always perfect, but almost right at the value we told the computer, hey, this is my null hypothesis. So we should expect that if we draw this picture, we simulate whatever, we will have the middle be our 695. That's from our null. And then what we can do is we can use the theory to fill in the rest of this picture. And so what the theory says is, okay, your middle will be there, good. Then if you take one step to the right, how do we do that? What do you mean one step? It's one standard deviation up. So we go one standard deviation up, that'll be 698 and some change. How did I get that? I start with 695, I add one standard error to the right. I do it one more time, I get to 70152. These numbers help me see that most of the samples will fit in between here and here. So look at the picture. Almost all of our samples will fit in between 2 standard deviations left and 2 right. And this is going to happen every time. Every time we use the theory, whether it's for quantitative, categorical, doesn't matter, we are going to see that if we just find the middle from our null and we go 2 standard deviations up, 2 below, we're going to see that we have almost all of the samples fit in that range. Pretty crazy. Okay, so we set this picture up and we're going to set it up the same every time. Take your middle, add a standard deviation, add a standard deviation. Take your middle, subtract a standard deviation, subtract a standard deviation. Okay, so we want to then calculate the standardized statistic for our sample using this information. So Our t-score, we're quantitative, so this is a t-score, is statistic minus the mean of the null, middle, divided by the standard error. Well, we have all that. Our stat is 710. That's what we got from our families we talked to. This was our claimed value. It's right here. And this was our calculated standard error. So we get a t-score of 4.6, which is huge. And that makes sense because look at 710 is somewhere way out here. That's very extreme. So very extreme, before what did that mean? It meant, okay, that means let's throw the null out. No way. We should think we've got evidence for the alternative. And if you go back and you look at how you interpret a t-score this big, you'll remember the cutoffs were if you're inside -2 to 2, then we're going to say null plausible. But if your z-score or t-score is outside that, it's bigger than 2 or less than -2, we're going to end up saying, okay, throw out the null, let's go alternative. And that's exactly what we're doing here. So it's somewhere crazy out here, pretty far away. Probably even further than that. Okay, so using that, what do we say? We have strong evidence that the average monthly grocery budget for a family of 4 in the U.S. is not $695. Okay, that's our going back to the conclusion. So in the next part, we're going to show how we can get the computer to take samples of our pretend population that we're assuming has 695 as its population parameter. We're going to take samples of size 115, and we're going to see what the distribution should look like. And we're going to compare it to our picture that we made from just our few calculations. So here's a picture of the applet. We had to click population model first to get this to pop up. Then we typed in 695 and 35. Those were our population mean and standard deviation. Again, we don't know these, but this was the claim, so that's what we're putting in. Then we're going to do 1,000 samples with a size of 115 because that's what we did. Our sample was that size. And what we end up with is this distribution here. So let's zoom in just a little bit so we can see it. And let's think about it. We've got a mean of about 695. That's what we predicted. We have a standard deviation, a spread here of 3.136, so 3.2-ish around there. That sounds familiar. Why don't we go up? So look at that. We got 3.26, super close to what the applet got, which was 3.2 if you round up just a little bit. So really, really close. Okay, now, so let's compare our picture we made using the theory to the picture that we got from actually sampling a population like that. 695 in the middle, that matched, but we'll go back and check. One standard deviation over is 698, and you can see that kind of defines a good chunk of the samples in the middle. And then one more over is 701.5, round up to 702. So why don't we go check these and see if it matches our picture down below. All right, 695 in the middle, 2 steps over, hit 702, and it looks like if we sliced there and sliced on the other side at about that same distance, we would have our usual chunk, and then we'd start to get unusual, which is exactly the picture that we found above. So we're right there. We've got it. Our simulation matches our theory. And so we don't have to take 1,000 samples of size 15 from this population. We instead can use the theory to predict this shape, its center, its spread, and then use our predicted distribution to get our t-score, do a p-value, get our conclusion.